everyone. My name is Julia Grassl, and I'm the program leader of the Honeybee Health program for the CSE of honeybee products. Today, I want to talk to you about the development for our AFB sensors. But first, I'd like to introduce my group and quickly talk to you about some of the other projects we've been doing for honeybee health and immunity, as well as nutrition. And then I'll finally get to the AFB sensor development. So our group has been built on the legacy of cyber and the work from Boris Baer. But now that we have been working for the CSE honeybee products, we really have had the opportunity to work with the beekeeping industry and to work on industry relevant and guided studies. So with that, for example, we started working with nutrition and also diseases, and we can do a lot of this work at our beautiful bee yard, and we're very fortunate that this is situated right in the heart of our campus. And obviously it is really sad that today you couldn't see this beautiful location with the university right by the river, and you can see our bee yard right at the bottom there, right in the heart of it. So that, on top of being located within the School of Molecular Sciences, we're really fortunate that we have access to a lot of tools and technology in molecular sciences, chemistry and biochemistry. On top of that, we have 15 years of experience with honeybee research, where we've developed a lot of tools and techniques to keep bees and experiment with bees that now we are really benefiting from. So one of the projects that we've been working on for a really long time, or at least where our work has continued for a really long time, is to determine what is a healthy hive. And we've been doing that through assessment sheets, looking at hive performance, comparing brood patterns and queen qualities, all these kind of things that you do as beekeepers as well. And then Shannon has been doing more and more hygienic behavior to really correlate some of the work she's doing on bee defenses and immunity, to correlate that with hive health factors. So if you want to hear a little bit more about that and how she's developing systems to compare resistant and tolerant bees in the future, head to her talk at 3 o'clock. In terms of nutrition, our changing environment and loss of our natural habitat has been making it harder and harder for beekeepers to find good floral sources to put their bees on. So supplementary feeding has become more and more important. And so in this project, we were looking into the effects of different treatment regimes. Clarissa has been studying the effects of supplementary feeding and how bees cope with starvation and poor nutrition at a molecular level. And her research is actually really, really interesting. So if you've missed the talk this morning, make sure you go back and watch it again, because beekeepers are doing more and more pollination, so finding good nutrition and supplement are becoming more and more important. And this kind of relates me to coping with diseases. Plant health and some of the agriculture sectors have developed many treatments. They have many treatments available to them for optimal nutrition, disease prevention, and treatment. But there's quite little available for honeybees. And so much of the efficacy and toxicity of some of these supplements and treatments is quite unknown or unconfirmed. So really, it leaves us with early detection for the best prevention and treatment options. And AFB is one of those diseases where prevention, or I guess isolation, a bit of a lockdown, has been really, really important. This here, AFB is one of those bacterial diseases that affects your larvae. And here on the left, you can see what the infected brood actually looks like. You can see the kind of dead brood that can turn into coffee-colored color. on the right, you can see cells that are slumped in and maybe pitted, have a little hole in them. And you can also see the rope test, where you stick a matchstick into an infected cell, and if it comes out like that rather than a healthy larvae, then that is a clear sign of AFB. However, for all of that, you have to open the hive. You have to inspect all the frames, look at the cells. Not only is that time consuming and you could miss something, it also poses a risk of contaminating other hives if there is AFB. So Jessica Moran has spent her PhD identifying the smells and the biomarkers of AFB. Beekeepers can smell AFB when a hive is heavily infected. And like any smell is actually made out of compounds. It's small particles, chemicals, molecules that float in the air, and that becomes the volatile profile. And identifying what is in that volatile profile and in the AFB air has been Jessica's PhD. She's discovered a range of biomarkers for AFB. And if you want to hear more about how she did that and her really fascinating work, head to her talk a little bit later at 3 o'clock. So we've been quite fortunate now that we started using some of these biomarkers that Jessica discovered, and partnered up with AgriFutures and the University of Western Australia to form a team to develop some sensors for the biomarkers that Jessica has discovered. And this is what one of those biomarkers looks like. On the left axis, you have the abundance of that particular molecule, and you can clearly see that there is a large amount of this particular biomarker or compound in air from AFB. And there's relatively little, almost none, virtually none in healthy brood or brood that has died by other causes, for example, overheating or freezing. And this type of biomarker is a great biomarker because it shows a clear signal only for AFB. And Jessica has gone through the validation process of identifying these or of validating these biomarkers with AFB brood isolated, but also in the hive. And yeah, her research is really cool. You can look at that. So now we have taken those biomarkers and actually look at them in isolation. And then we have used organic chemistry to develop chemicals that specifically bind these biomarkers. So here, for example, is a chemical that starts off with for example, with a purple color. And when it specifically binds one of the particular volatiles or compounds and biomarkers in AFB air, it actually turns orange and changes its shape and conformation slightly. So now we've done that for a number of biomarkers, developed different sensor surfaces, specific surfaces for a number of those, and each of them change color from a different color to a new color. They're quite specific. We've then gone away and measured the response of these biomarkers against the chemicals individually and isolated. But then secondly, we've gone to test them against AFB larvae in a vial. But what we haven't done quite yet is to test them in the hive. So we're still developing them. And this is where we are. We've developed so far, I think, 5 of these sensors against specific biomarkers. So this one on the top left, for example, it starts out as a white color, and as it is exposed to volatiles or AFB air, it actually changes to a blue color. And then the next one over to the right starts off again as a white color, and as it is exposed to AFB air, it turns yellow. And the bottom ones are going from purple to yellow or black to orange in a similar way. So we've built in some kind of redundancy using multiple sensors that react to quite different biomarkers to make the potential test a bit more reliable. And this is work been done by a brilliant postdoc, Praveen, She's a chemist and she's been working really hard on this. So what Praveen did next is she actually looked at selectivity, specificity of each of these different sensor surfaces. And on the left, you can see that they start off yellow, this one, and when it is exposed to a healthy larvae sample, in the middle, it remains yellow, but when it gets exposed to AFB larvae, it clearly turns orange, and it does this quite quickly. And then, so we have got some selectivity here for the markers. The next step is to look that there's some reproducibility. She's developed these sensor strips over and over again for each of the biomarkers and made sure that they always have the same color and that they always change to the same color within a range when they're being exposed to AFB volatiles. And in the next step, we're looking at the stability of these strips, because of course they have to be able to be stored and sold and stored by you as a consumer, for example. So one next experiment she has been doing and is still doing is to make these strips and then leave them out in the air for longer and longer periods of time and make sure that they then still work after a period of time. So we're getting there, and we can get kind of a bit more information and increase stability for each of the sensors. And then the last step, we are looking at kind of sensitivity and speed, which means that we of course these strips and sensor surfaces have to react to really small amounts of AFB in the hive, and that is in obviously in the hive where there's lots of smells and only a couple of cells of AFB, and this has to happen relatively quickly for them to be useful, and that's something we are still working on. Now I want to show you what this could potentially look like. A similar technology was developed for plant diseases. I don't think it's actually on the market, but there was a really interesting paper in Nature Plants a couple of years ago, where they've done something similar using different chemistry, but a very similar approach. They also developed kind of paper strips with different sensor chemistry spotted on top of the strip, and then these strips are exposed to plant diseases on a leaf, and again the colors change. And then using a smartphone and the camera and the flash from the smartphone, you can take a picture of the sensor, of the colors after exposure. It could be then compared to an app that lives on your phone, and using like a calibration chart and a bit of computer algorithms, the colors could be converted into numbers and signals, and you could get a result. If you want to compare that to something that you're probably already using right now, if you're thinking about your pool test strips, on that you have different types of chemistries. You have something that shows you the amount of chlorine you've got. You've got something else that shows you the amount of the pH, or how alkaline your pool is, the hardness of your water, and a number of other things, all in one strip, and use the color, and you compare it again to a chart, and you know where you are. So imagine that instead of a scenario that you have here on the right, where you are employing dozens of people to check all the hives and before you are entering a large pollination event, for example, checking for AFB and other diseases. Wouldn't it be lovely if you could suck out some air from the door from the hive and expose a disposable paper strip, for example, and get a signal and a readout within a short period of time. We not actually commercializing this at the moment. This is kind of something in the future that we have to find. We have to find some commercialization partner, people actually who do this really, really effectively, because in the end of the day, we are scientists and we remain to be scientists. But I think this has great potential to be commercialized. I'm envisaging that the strips are disposables that you can buy, and yet you buy the small device that sucks out or pumps out some hive air into a container where the strip is then exposed, for example. You use a new strip for every hive, and you upload the images on your phone to an app, and should get an answer really quickly. So this is kind of where we are. And I hope that we will make really good progress really quickly to get this to a stage where we can commercialize it and bring it as a product to you. So that just leaves me to thank my team and thank everybody we've been working with. I am extremely proud of our students and postdocs for working so hard on this and achieving this and allowing me to present this to you today. And of course, I would also like to thank the CRC, Honeybee Products, and AgriFeatures for making all of this possible. And lastly, I'd like to thank you for not for coming, but for listening and persevering with us, even in this kind of lockdown situation. And please let me know if you have any questions. Thank you.